Okay, so before we talk about applications in general, we are going to study how to use the infinitesimal method to set up the integrals first. Okay, so basically, infinitesimal method is used to set up the integrals for computing many quantities in other senses, engineering, and many other things. The big idea is a quantity can be calculated by integrating approximations of its tiny partial values. Just remember the basic idea first, and then the meaning will be clear later. The step procedures for infinitesimal method is on the screen. I will use a particular question to show you how to follow the step procedures to set up an integral to compute some quantities. The first quantity we are going to compute, we are going to set up the integral, is the area between curves. Now look at the question on the screen. We'll go back to the step procedures and follow the step procedures to set up an integral for the area of the region enclosed by two curves and two vertical lines. The plane region is something like this. I'm going to draw a sketch. You have a horizontal axis. I'm not going to draw the vertical axis. I'm going to use X to denote the horizontal axis. There are two curves. The first curve is the top curve. The top curve is the graph of that function, y equals f of x. You have a top curve, something like this. And the g of x is the bottom curve of the region. So because you have the condition f of x is greater than or equal to g of x, so the graph of f of x is above the graph of g of x. Right. Now let's say that's the graph of f of x. The equation is y equals f of x. There's a graph below that, which is the graph of the function g of x. Something like that. Okay. The bottom curve is the graph of g of x. I will write the equation y equals g of x. And also there are two vertical lines. One vertical line is the vertical line x equals a. Both functions are defined on the interval from a to b. Okay. One vertical line is the vertical line passing through this point on x-axis. This is x value of a, so that's x value of b. Okay. Two curves, a top curve, a bottom curve, and together with two vertical lines enclose a plane region. The plane region is something like that. I will draw dotted line here, probably. Okay. You have another line, the vertical line x equals b. X equals b. It's a vertical line, something like that. Again, I will draw dotted line in here. I want to repeat two curves and the two vertical lines, they enclose a plane region. Now we are going to set up an integral for the plane region, something like this. We are going to follow the infinitesimal method on the screen. You have three conditions to verify. I will mention the meanings of the three conditions one by one. The first condition is every subinterval of AB corresponds to a unique partial value of Q. Now we are going to use Q to denote the area of the region. I know in general the area of a region is denoted by A, but to be consistent with the notations in the in the step procedures, I'm going to use Q to denote the quantity, to denote the area of the plane region. The first condition is every subinterval of AB corresponds to a unique partial value of Q. The condition is actually, now let's say we imagine there's a subinterval of AB. The subinterval has now let's say this point has x coordinate of C, this point has x coordinate of D. Okay, so we have a subinterval CD from C to D. That's a subinterval of AB. The condition is that every subinterval, now let's say the subinterval from C to D, corresponds to a partial value of Q, the total area. The partial value is not hard to imagine. The partial value is actually the area of the region in between the two curves over the interval from C to D. I'm going to draw a sketch. The partial value is the area between the two curves, the graph of f of x and g of x, over the interval from C to D. The area of that region. I'm going to shade that. Now the area of the shaded region is the partial value corresponding to the subinterval from C to D. CD is the subinterval from A to B, right? That's the first condition. Every subinterval corresponds to a partial value of Q. The first condition. The second condition now is the interval AB, the total interval AB corresponds to the total value of Q. That condition is of course true in this particular case. Right. If you treat the interval from A to B as a subinterval from A to B, then the value, partial value from A to B is of course the total area. In this case, the total value of Q, right? The second condition is automatically satisfied. Now the third condition. The third condition says Q is additive over disjoint intervals. It means you imagine you divide the interval from A to B into many subintervals. And then each subinterval corresponds to a partial value of Q. You add up all such partial values. The total of all partial values should be equal to Q, the value we want to compute. You can imagine the condition is of course true. Okay. If the three conditions are all true, then we can use the infinitesimal method to set up the integral for the total area. Actually, in general, for most quantities we are going to compute, the three conditions are all true. So in many cases, you do not have to verify the three conditions. Now we are going to follow the 3 steps to set up the integral to compute the area, the integral for the area of the plane region, the area between the two curves over AB. It's not selecting. I think now it's selecting. Now step 1. In step 1, we take a subinterval of AB. The left endpoint is x, the right endpoint is x plus dx. You just imagine x is an arbitrary point on the interval. Now let's say x is here. You imagine x is an arbitrary point on the interval from a to b. And then to the right of that, you have a point x plus dx. In general, you imagine dx is a very small number. In this case, we just imagine dx is a very tiny positive number. Again, I want to repeat, you take a tiny subinterval from x to x plus dx. And dx is a very tiny positive number. Temporarily, we make the thing a little simpler. Okay, and the subinterval corresponds to a partial value of Q, which is the area of the region between the two curves over the subinterval. I'm going to call the region in between the two curves over the tiny subinterval a curved trapezoid. Okay, I'm going to write something down. Maybe the solution to how to set up the integral for the area. Okay. We let delta Q, delta is the uppercase Greek letter, it's called delta. We let delta Q be the partial value corresponding to the interval, the subinterval. The partial value of Q corresponding to the subinterval. The subinterval is a tiny subinterval from x to x plus dx. It's actually the area in between these two curves when over the interval from x to x plus dx. The area of the indicated region. Okay. I do not want to do too many shading, so later on it could be a little messy. I'll try to give it a description. I'm going to call it the area of the curved trapezoid. You see it's kind of upside down trapezoid, but you have two curved sides. Okay. You can imagine it is the area of a curved trapezoid. That's step 1. I can label the step. The next thing we do is to approximate the partial value over the tiny subinterval. Our target is to approximate the partial value using a function of x then times dx. In general, the way to approximate is to use something constant to approximate something various to use something straight to approximate something curved. I will show you what I mean. Now the partial value of Q is the area of the curved trapezoid. Now we are going to approximate the partial value using the area of a rectangle. I will tell you how to form the rectangle. Okay. I'm going to make the full size of the rectangle solid. Okay. The rectangle to be used to approximate the curved trapezoid is given by the following. The height of the triangle is that, the solid line segment. Okay. Maybe I'm going to label the points using some letters. I will call this point A. I will call this point B. Again, the rectangle has the height of AB. Of course, the width is dx. We are going to form a rectangle using that side and also using the width of dx. Okay, you have something like that. Again, we are using something straight to approximate something curved. We are using the area of the rectangle as sketched to approximate the area of the curved trapezoid. We'll see what's going on. Okay, our target is to write the partial value of Q, so delta Q, approximated as a function of x times dx. Now let's see if we can do that. Where on step 2, we are going to find the approximation of the partial value of Q in terms of a function of x and dx in that form. Okay. Again, now let's recall the notations. Delta Q is the partial value of Q corresponding to the interval from x to x plus dx, corresponding to the tiny subinterval. Okay. This area can be, this partial value, the area of the curved trapezoid, can be approximated using the area of the rectangle. Now we need to get the area of the rectangle, we need to identify the width and the height. The width is easy. The width is actually dx. The width is dx, the length of the tiny subinterval, right? The length of the tiny subinterval is dx. Now all we need is to get the height. Now let's say point A is on the curve, point B is on the curve. So A has x coordinate. I'm going to write it down. A has x coordinate. Point A has x coordinate of x, and y coordinate of point A. Because the point is on the curve has the equation that y equals g of x. So point A has x coordinate of x and the y coordinate of course, g of x. Likewise, point B has x coordinate of x. X is here, right? Point B has x coordinate of x and the y coordinate of f of x. Now the height of the rectangle is actually the distance between these 2 points. The distance between these 2 points, of course, it's f of x minus g of x. I'm going to write it down. Okay. Delta Q, the partial value corresponding to the tiny subinterval is approximated by the area of the rectangle. Thus the width of the rectangle dx. Now the height is given by f of x minus g of x is the difference between the y coordinates of point B and point A. Now let's go back to the step procedures. Now we have achieved that. By that I mean now we have approximated the partial value of q as a function of x times dx. In this case, the function of x is f of x minus g of x. We have achieved that. If we can achieve that, in step 3, the total value of q, the q in this case is the area of the region between the two curves over the interval from A to B. The total area of q in step 3, the total area of q now can be computed is equal to an integral. We set up an integral for the total area. Total area is q, the area between two curves. Okay, so q is computed. The interval is the interval from A to B. Of course, the integration is taken from A to B. Okay, so q is computed using the integral from A to B. We integrate this part, the integral from A to B, f of x minus g of x, then dx. Finally, I want to make some comments on infinitesimal method. The first comment I want to make is that the approximation in step 2 applies to any value of x, wherever x is in the interval from A to B, as long as dx is tiny. The second comment is that look at step 2. In step 2, the left-hand side is a tiny partial value of q. On the right-hand side, you have approximation of the tiny partial value of q. The last step, it means q can be calculated by integrating the approximations of tiny partial of q. This is consistent with what we mentioned at the beginning. Now look at here. Infinitesimal method. A quantity can be calculated by integrating approximations of its tiny partial values. Lastly, the infinitesimal method is not very mathematically rigorous, but it works in most cases as long as the approximation in the second step is reasonable. In fact, the infinitesimal method can be translated into a rigorous treatment by forming a Riemann sum.